Welcome to this next module titled Reintroduction to Engineering. Now, what does that mean? I wanted to take some time to go over a number of topics, for example, linearity, linearization, Taylor series expansion, topics that you should have learned in prior classes but perhaps aren't so fresh in your mind right now. And I thought that we should do that now, earlier on in this course, before we dived into later topics which may need to reference that material. So that essentially is what this is. It's a review of topics that I think will be very important to later modules of this course. Now, this lecture does include a lot of homework. I haven't really decided 100% how I'm going to treat the homework, so I'm not going to simply just post the solutions here as part of the lecture, but I am going to try to find a way to post solutions in some way, shape, or form. Like I do normally, I have a YouTube link here that I encourage you to check out. You can get to that link by essentially downloading this PDF from the description below, and then you can click on the link from the PDF. All right, so we have a number of exercises to take a look at. The first one is simply just called basic algebra. So circuit analysis is a very algebra-heavy course, and there are going to be, especially when we get into nodal and mesh analysis, there are going to be many instances where you have sets of linear equations that you need to solve. And so this first homework problem right here, although I'm not going to show you the full solution, it tells you something that you should be familiar with how to solve problems like this before you can tackle circuit analysis. I'm hoping that most of you will see this as being relatively easy. One easy way to solve a problem like this, right, is to simply make a substitution where we say y is equal to 500 minus 0.1x, and then we can substitute that into the other equation, which gives us 0.35x plus 500 minus 0.1x over 5 equals 250, right? And this gives us an equation that's a function of only a single variable, and so I'm not going to show it, but you could solve this and determine what the value of x is, and then plug that back in to get the appropriate value of y. Okay, so basic algebra, obviously something you need to be very strong, have a strong background in to succeed in this class. Another related topic is going to be linear algebra. Now, for my students at the College of New Jersey, there's a course called ENG 272 Advanced Engineering Math 1, which teaches them this material. I recommend that you have taken some sort of linear algebra course before you try to dive into circuit analysis. What we're going to do here is give a very brief overview. So linear algebra. Linear algebra is essentially the idea or the study of these types of equations, matrix and vector-based equations. So we know that a vector or array contains a single row or single column potentially within a larger structure. So we have X has a length of 5, it contains 5 elements, and these are just ways of referencing various elements. X2 is 9 or x sub 2. I mean, the notation really depends on your preference, but these are the ways that I normally index arrays. A matrix contains multiple rows, columns, and orthogonal layers of real and complex values. And so here we have an example of a matrix. This is a 3 by 3 square matrix, and you can see here I've shown the indices for the individual elements. Now, MATLAB is an important part of this course. There's another module that we talk about MATLAB explicitly. And so what I've done is thrown in MATLAB commands for some of these ideas or for some of these objects. This is how you would define a similar matrix similar to this up above in MATLAB, where essentially use the semicolon to separate rows of the matrix. And you can use a command like this right here, because we called this matrix X. And so by referring to matrix X, open parentheses 3, 2, that gives us the third row, second element, or second column, which is 6. Now we can perform addition and subtraction of matrices. This is relatively straightforward. Okay, any two matrices or vectors can be added or subtracted as long as they have the same dimensions. And the reason why this is the case is because you literally just add or subtract the corresponding elements to one another. Here is a MATLAB example. We have one matrix X, another matrix Y, both of them being 2 by 2 matrices, and so we can add the two together and it ends up giving us a 0 because one is simply the same as the other except multiplied by -1. We're not going to talk too much about performing these operations by hand. However, I will show you in very brief terms how to do that. Multiplication can be a little bit more complex. So for multiplication, the rule is essentially if you have a dimension of alpha times beta and you want to multiply that matrix times another, which is beta times gamma. So the size is alpha by beta and the size here is beta by gamma, where alpha is the height, beta is the width, beta is the height, gamma is the width. Now, why do these two values match right here? Why do I use the same letter? Because in order to multiply those matrices by one another, those elements, those dimensions need to agree. And so down here below, you can see where we actually execute this multiplication. So we have a 2 by 2 and a 2 by 2 matrix. The result of this multiplication will also be a 2 by 2. So if I go back up here to my example, where we had an alpha by beta times a beta by gamma matrix, what is the size of the resultant? It's going to be the outside indices, so an alpha by gamma. So that is going to yield an alpha by gamma sized matrix. Over here we have a 2 by 2 times a 2 by 2, and so our result is also going to be 2 by 2. Now how do we do this? We essentially take, to yield the element 1, 1, the first element, the top left element of the resultant matrix, we take this vector and multiply it by this row right here. Hence, that's why you see x1 times y, well, x11 times y11, this element times this element, plus this element times this element, x12 times y21. For this element right here, which would be the resultant 1, 2, first row, second column, that's going to be the same row, but now we multiply it by the blue column, and on and on. So the way that we do this in MATLAB, I mean, it's relatively straightforward. All you have to do is create the matrices and then multiply. Let's try coming up with one of these values on our own, however. So we have 1, 1, 2, 2 times 1, 2, 3, 4. Okay, so what is that going to give us? So for the top left element right here, it's going to be this column times this vector. So that is going to give us, let's see, that's going to give us 1 times 1 plus 3 times 1. So hence 4, and that matches what we have over here. Let's try one more. Let's do this element, which is going to be this row, that column times this row. So that's going to give us 1 times 2 plus 3 times 2, which is 6, plus 2 equals 8, and we have the corresponding value down there. Algebra, linear algebra, a huge part of circuit analysis. If a lot of this looks like Greek to you, it's completely outside of your regular wheelhouse, then I really recommend you find a resource to review that linear algebra material. Now, division is done in a very similar way to multiplication. Essentially, we just multiply by the reciprocal of the value or by the inverse of the matrix. There are some by hand methods that can be used to invert matrices. We're not going to go over those here. Here's a homework that you can check out and try on your own. We can give you one of the values real quick. Let's calculate the top left value. Well, first let's look at the sizing. So this is a 2 by 3 matrix times a 3 by 2 matrix. All right, so these dimensions agree, so that's good. That means we can multiply. And the resultant will be a 2 by 2. So we're expecting to have something like this. Now let's just calculate one of those values, the top left. So the top left will be this column times this row. So it'll be 0 times 3 plus 1 times 4 plus 6 times 5. So that's 34. And then I'll leave it up to you to come up with the other 3 elements. How this relates more closely back to circuit analysis is the idea that we can represent a set of linear equations as a matrix equation, a single matrix equation. And so an example we have is right here. Imagine we have ax plus by equals c. I don't need to write the rest of this. It's all shown right here. How can we convert this into a linear algebraic form? You see that the variables here are shared, and so we can extract those, x and y, and then move their individual coefficients to a separate matrix. Everything on the other side of the y, of the equal sign, can then be pushed into its own vector. So these two are equivalent to one another. And the nice thing about this form is now we can use matrix algebra to solve. So I've named these matrices alpha, beta, and gamma. So let's say we're trying to solve for beta. Let's say this is unknown. We can essentially say beta is equal to the inverse of alpha times gamma, as shown over here. And that will solve and generate a solution for us. This is going to be the basis of your nodal and mesh analyses. We are going to take a relatively complex circuit and put it into a form that looks very similar to this up here. We have another homework, represent the algebraic problem below in a matrix form, then use MATLAB to solve. Do you get the same solution as you did above in the first homework? So this is the same problem that we already addressed above. The only difference is we have to put it into a linear algebraic form. I'm not going to give any clue on this because honestly, if you see this structure here, it should become pretty obvious how to make that translation. For example, this A is simply 0.1, right? And then you have X and Y, and you can make the rest of the moves yourself. Next topic is state variables. So this lecture may seem to be a little bit disjointed, but again, the idea here is to touch upon topics and concepts that you should have already been familiar with, or you should already be familiar with, but that I've realized a lot of students are not necessarily even weak on, but it's just they need a little bit of a reminder. So let's talk about state variables. State variables are a set of values that describe the quantitative and mathematical state of a system. Those states should allow one to fully describe the system and, if dynamical, predict how the system will change in the future absent of any external forces. In short, the state variables are a minimum set of quantitative values that tell us everything that's going on in the system. It doesn't necessarily give us every single value. So for example, for a circuit like this, generally we consider the state to be the set of voltages. But we could also ask questions about the currents or the power being consumed by certain elements. Why aren't those part of the state? Because the voltages are the minimal state of values that we need to calculate the others relatively easily. Once we have the voltages, we have closed form equations, closed form solutions that allow us to generate the others. So in electronics, generally the node voltages or branch currents describe the state of an electrical system. So here we have a basic circuit. We see that all voltages are measured with respect to a common reference, which may be ground, so our reference is here. And we can calculate all other values, power, energy, currents, all from knowledge of V1 through V6. We have V1, V2, V3, V4, V5, and V6. If we know those 6 values, plus we know all the additional resistances and capacitance values, then we can calculate anything else that we need. Variable types. Constants are just that. They're constant. These unchanging values generally describe knowns such as resistance or mass, and they are not expected to vary. Time-varying functions or variables change with time. Static variables don't. So a static variable, which normally we would associate with, let's say, voltage within a DC circuit, would be Vs, and then time varying would be Vs of t, or Vs of k. The only difference being here that that one is generally a description of continuous time, and this is a description of discrete time. For most of this course, we're going to be dealing with static DC voltages, but there is an AC portion to it. Hopefully the terms input and output are self-explanatory. Obviously one goes in, one comes out. We can also use independent and dependent variables there. Or that's actually the next topic. So independent variables are those which we control. They are expected to drive the system, determine the range and domain of the problem, and they may be used to generate a set of dependent variables. Generally, independent variables correspond to input and dependent correspond to outputs. So let's say I have a circuit that looks like this. All right. More times than not, your source is going to be considered to be your input or your independent variable. And let's say, for example, the power consumed by a given resistor, that could be an output, okay, or a dependent variable. Now, the definitions of these terms and how they're used will differ depending on the application. Now that we've talked about independent and dependent variables, let's talk about how to make a proper graph. This may seem rather elementary, but it's needed for many students. How do you make a proper graph? First things first, you want to have your independent variable on your x-axis, and you want to have your dependent variables on the y-axis. So here we have V in, we have P out. You'll want to give units to both axes so we understand what the range of values is. It's not shown explicitly here, but obviously you need to label the x and y axes with numbers which give reference to the data. And right next we simply graph our data. If you have more than one line, then you should have some sort of a legend or a key which does so. And then lastly, it's important to have a good title. So I would say that a good format for a title is dependent variable versus independent variable for some system with constants A, B, and C. So let's say we're talking about a circuit. Let's say we're talking about a circuit that has a dependent value, which is the power consumed by some resistor. The independent variable could be the source Vs1, and this circuit would be, we'll call it a power regulation circuit or a regulator. And then let's say we'll set some constants, maybe the I maximum current is 10 amps. So if we have these values right here, I could create a good title, which would be power consumption for load versus VS1, or you could say applied voltage for power regulation circuit shown in figure X, and an I max of 10 amps. Now I just made this up off the top of my head, but the objective here is to demonstrate that titles are really important. The thing about a graph is that it's only as good as it is understandable to a third party. Something may look very good for you, or let's say someone on your team, that's familiar with the data, but if it cannot be understood by a third party strictly by looking at it, then you don't have a very good graph. So I encourage you to look at other formats, other examples online, but I've tried to lay out something here that's a pretty good base version of what a graph should be. Next, let's talk about modeling. So modeling is a huge part of electrical engineering and a huge part of circuits. A conceptual model is a representation of a system. It may be represented mathematically as a transfer function, which describes the input-output relationship. Here is a really basic transfer function where the output is a function of x is equal to some function, which is 3x in plus 4. That doesn't really correspond to any physical system, but it's an example of a transfer function. Now, different models with differing levels of complexity may be used to describe the same system. This is especially obvious or evident in a course like electronics, where for something like a MOSFET or for something like a diode, we may have 3 or 4 different models that we use in different situations to represent that component. One model may be optimal for one situation and an alternative for another. In many cases, for example, we model solid state switches as instantaneously toggling between 0 and infinite resistance. And this is good enough for many applications. However, sometimes it is necessary to consider the switching actions themselves, which are not instantaneous, and consider the resistances that lie in between the ideally 0 and infinite resistance, right? Because a switch does require some time to open and or close. And if we're looking at a transient over a very short time period, where that time window is on the same scale as the length of time required to open or close the switch, then we have to consider the effect of the switch on it. So if we look here, we have a battery, and we have the most basic model of a battery, which is simply just the voltage source. If you remember one of the previous lectures, I used this to represent a battery, which is slightly more complex, including an internal resistance. Sometimes that's needed, sometimes it's not. Okay? So something like this is fine when modeling the battery as a supply for a circuit, assuming that the charge is greater than 50% and that the internal resistance is very small and or negligible. However, we need something more complex for something like a battery charger. So this model right here is not going to be an appropriate way to model the component if you are looking at interaction with the battery charger, because the battery charger relies on the idea that the voltage differential between these two nodes is going to drop as the charge leaves the battery. Next topic. So this one I can't overstate. Problem solving. Problem solving is an absolutely essential part of being an engineer. There are so many good methods to solve engineering problems, and there's tons of books that have entire chapters on this. I've kind of amalgamated them into one set of these following steps. So define the problem, list the possible solutions, evaluate and rank the possible solutions, develop a detailed plan for the most attractive solutions, reevaluate the plan to check desirability, implement the plan, and check the results. So, for many engineering problems, you may not need to go through all of these steps. The reason being, if it's a relatively straightforward problem, one that you've seen a lot of times before, you may already be familiar with what the most attractive solution is going to be. If I give you a circuit, okay, with independent sources and constant resistances, and I tell you I need to know what the total power consumption is for all the resistances, you don't need to rank possible solutions there. I mean, it's pretty straightforward. You can use something like a nodal analysis to solve, and then you just have to simply calculate the power consumed along all the different lines. So this is a very, let's say, generic process up here. If you're talking about something like your senior project where you're looking at more complex problems, then you may need to use all the steps. Now, I think the most important thing is to consider all of them and to take a methodical approach to problem solving. And this is something that you have to train yourself to do. I mean, there's one thing to understand these steps right here, but implementing them in an effective way, that is a little bit different, right? You need to practice. It's like playing an instrument. You need to practice in order to get a better understanding of how to apply it. And that's the reason why in your classes we give so many homework problems, and the reason why you have quizzes, and the reason why you have exams is because practice is the only thing that can teach you this. Now, there are often barriers that prevent us from considering all possible solutions. Those barriers include confirmation bias. This involves us bending facts to reach a preconceived result. Perhaps you are building you're building a voltage regulator, right, for some sort of charging a laptop. When you test it, you need to be careful of confirmation bias. You may be looking to see the thing working. You may be expecting it to work, and therefore not essentially opening up your eyes to the fact that, okay, hey, this output voltage, although it's regulating, it has a huge ripple in it. Or it only works some of the time, and half the time it gives me a different value. So you have to be careful with confirmation bias. Also, unnecessary constraints. This involves making unnecessary assumptions to the process, or associating unnecessary assumptions with the process. Does a value have to be positive? Okay, am I limiting potential solutions that I could be considering? And this comes up all the time in circuit analysis, where essentially we may assume that we can only use certain components, or that we have these maximum and minimum values, but they may not be the case. There's also irrelevant information, and this is a trick that a lot of professors will throw at you on exams. I know it's something that you see on the FE exam, you see it on the SATs, the GREs. So irrelevant information is a barrier because it makes you consider unnecessary constraints. So let's take a look at this. For example, 15% of people in New Jersey have unlisted phone numbers. If you randomly pick 500 numbers from the phone book, how many will be unlisted? Perfectly logical problem. And since I'm framing it as something where there's irrelevant information, you're probably catching the trick, which is that if you pick 500 numbers from the phone book, none of them are going to be unlisted, obviously. But your brain will often default to just saying 500 times 15%. That must be the number of unlisted numbers. And so you have to be careful to avoid pitfalls like that. So let's take a look at an example. We are designing a system that can generate a current between 1 amp and 10 amps. This current flows through a heating element which we want to emit approximately 1300 watts. Unfortunately, the resistance of our heating element is nonlinear, okay? Meaning that R is not a function of the terminal, meaning that R is a function of the terminal voltage difference, V. What current value, I, generates the desired heat output? This does not require any electrical knowledge because we can simply rely on the math below. So you can see this is a similar problem that very similar to what we saw in the practical engineering problems section. Because again, I want you to focus on learning how to think like an engineer, not just how to solve circuits. So let's take a look at these two equations that we have. The first one is P equals I squared R. This is derived from P equals VI. We can replace the V with IR, which then gives us I squared R. So that's where that comes from. All right. So we're told in the problem description that this should equal 1306 watts. And we're tasked with trying to determine what the appropriate current value is. If R were constant, we could simply invert and we would end up with I being the square root of P over R, or the square root of 1306 over whatever that resistance value was. The reason why we can't use a description like this is because our R is a function of I. So when we solve, we do not end up with a closed form solution, an explicit closed form solution. We end up with an implicit equation where I is present in multiple locations. Okay, so we can't solve like that. And the reason is because of this expression up here. So Ri is not just equal to 10 ohms. Okay, that's not the value. It's equal to the maximum of two different values. It's either 10 or 5 plus I over 0.975. So we need to take this and plug it in right there, and that makes solving a little bit more difficult. Now, there's lots of different ways to deal with problems like this. This is what I would call a slightly nonlinear problem. It's not highly nonlinear. But this is a module that's really just preoccupied with logic. So let's not worry about trying to be very efficient. Let's just see if we can find a logical way to tackle this problem. And I've done so in MATLAB. So what are the logical ways of doing it? I mean, we could try some sort of Newton-Raphson based approach to this, but that's a little bit beyond the skills that we've developed in this class. What if we just simply cycled through current values and then stopped when we ended up matching our desired power of 1306? Let's take a look at that. So here I have a MATLAB script. I just cleared the memory. I'm setting up my increment. So what I'm saying is that my increment is going to be 1 milliamp. The smaller the increment is, the longer it will take, but also the more precise answer it will give. Let's determine the number of iterations we're going to need to examine the entire range. It seems here that we're going from 1 to 10 amps. And if we divide by the increment, which is 1 milliamp, we end up with the number of, essentially the number of increments, the number of iterations we would need in order to solve this. Did I say it was the limit was 10 up above? I guess not, but we're assuming that it's not going to go higher than 10. Now, what we've done is created a for loop, and we're going to cycle through all the different values, starting at 0.001 amps, then 0.002, 0.003, on and on and on, up till 10 amps. Actually, we started at 1, so it's going to be 1.001, 1.002, 1.003. Okay, so next we calculate the current value that corresponds to this increment. So it's 1 plus k times increment, hence this right here, right? For the first value of k, we'll have 1 plus 1 times 0.001, which gives us that. So we have our current for this iteration. Then we're going to calculate the resistance, but we have to do so in two parts. First, we calculate what I'm going to call Rx of k, which is this is the variable component. It's the variable piece of this down here. So we calculate that value, and then we use an if statement to check whether that Rx value, if it's less than 10, then that means we should simply return a value of 10. Now, why is that the case? Because remember, we're looking for the maximum. So if this value is less than 10, we use 10. If it's greater than, then we return whatever the original value was up here. So if this value is big, it will be used in the next expression. If it's smaller than 10, then what will end up happening is a 10 will be plugged in right there. Okay. So now that we have our resistance value, we have our current value. We go ahead and calculate power. This is the I squared R. And then this last piece right here, we're simply just going to check to see when PK exceeds 1306 watts. Because when it does, we know that we've received our answer. And so that's the end of this little mini algorithm here. Another good practical example of how to solve an engineering problem just by using logic. All right, linearity. So switching gears a little bit, I did want to talk about linearity. It's important because, one name for this course, I often call it just circuit analysis, but the more complete name would be linear circuit analysis. So what is a linear system and what is linearity? Let's refresh our memory on that. Linearity describes a mathematical relationship or function that can be represented as a straight line or a flat multidimensional plane. And the same characteristic descriptor, linear, that we use for a mathematical system can be described to any physical system which is represented or modeled using a linear function. So a linear process may shift or scale a signal, but proportionality must be maintained. So if we look here at this example of a linear operation, we have something that looks like a little pyramid with this weird shark fin. And although the output, right, we can make it taller, we can make it shorter, right? We can move it to the right, we can move it to the left. We can do any sort of shifting and scaling as long as it keeps the proportions of the input and the output. We expect the shape to be maintained. Now, that's a rather heuristic, or let's say layman's description of linearity, and we can do better than that, right? Because the real definition of linearity is going to be based on the superposition theorem, which we're going to talk about in a second. So, why do we even care about linearity? Linear processes are often preferable for EC relevant designs. Now, the reason for that is because they maintain the information, more or less, that's contained within the signal. A linear amplifier maintains the sound and tone of music, while a nonlinear amplifier may introduce distortion. I think the music example is a good one, because for a song, it still sounds like a song if it's louder. It still sounds like a song if it's softer. It still sounds like a song if you start it later or start it earlier. But it's the shape of those waves that determines how the song sounds. And that's what a linear process maintains. So a voltage amplifier would be one type of linear element or linear component for which that linearity is very important. So here we take a look at the graph of a transfer function for a somewhat pseudo-linear component. And what we see is that in this range right here, it acts linearly, right? There's a linear relationship between y and x. This is a constant, the slope. However, past this point, it enters saturation. And we call this the nonlinear region, because it no longer maintains this same slope right here. And this is what we see in a real-life amplifier, right? In a real-life amplifier, if this down here is Vin, right, it cannot generate an output indefinitely. It will be limited by essentially what the VCC plus what the supply voltage is. Linearity is generally an ideal characteristic. What we mean by that is it can be hypothesized or thought about in a theoretical ideal way, but there's very few practical real components that are completely ideally linear. Now, I talked about the superposition principle earlier, and let's go back to that. So let's say we want to test whether our system is linear, but do so in a more formal fashion. Okay, we can apply the superposition principle, which says that if these two sub-principles, characteristics, are maintained, then our system is linear. There's additivity and there's homogeneity. So as you can see, if we have a function, and this could be anything, it could be, x squared plus 3. Okay, it could be natural log of x, anything. Additivity holds if f of x1 and f of x2, and these can be any values, if that is the same as f of x1 plus x2. So let's try that for this function right here real quick. So we have x1 squared plus 3 plus x2 squared plus 3. Does that equal x1 plus x2 squared plus 3? No, it does not. And so that is not a linear function. It doesn't need to violate both of them in order to be nonlinear. It only needs to violate one of them. We also have homogeneity. Homogeneity states that if we take a function and we multiply the output of that function by a constant, that should give us the same answer as if we multiply the input by that same constant. So let's try it again for our function over here. We have alpha times x1 squared plus 3. Is that the same as alpha x1 squared plus 3? No, it's not. So that doesn't apply. And so, if a function satisfies both additivity and homogeneity, then we can say it satisfies the superposition principle. And the superposition principle is simply just a combination of additivity and homogeneity. A function y equals mx plus b is not linear unless b equals 0. A function like this, which appears to be linear, often people mistake it for being linear, is called an affine function, not a linear function. We have another homework here, which asks us to use superposition to determine that the function below is linear. And so, you could test additivity and homogeneity separately, or you could just apply the superposition principle outright. Give you a little bit of a starter there. Let's say we wanted to test homogeneity, right? That means that alpha f of x should be equal to f of alpha x. So that means that 3 times, I don't know why I chose 3. Alpha times 3x plus 4x over 9, that's our f of x, should be equal to 3 alpha x plus 4 alpha x divided by 9. Because over here, right, we inserted the alpha as a coefficient of the x value itself. Fortunately, we can pull these alphas out and group them, and we would end up with the same answer. So that shows that additivity is, that characteristic does apply here. All right. Next, linearization. So linearization is another important topic for you as an engineer to comprehend, to understand. We have seen before that nonlinear equations can be more difficult to solve than linear ones. All right, we generally are not able to generate a closed form explicit solution from a nonlinear equation. Well, that can be the case, and so that's problematic. If you look here, right, you have a nonlinear equation, you have a linear equation, and it's kind of a no-brainer which one is going to be easier to solve. But for better or for worse, nonlinear phenomena do exist, and they're very prevalent in nature. So we need models that utilize nonlinear components and functions. If only there was a way to make a nonlinear system act linearly, to linearize it. Well, we're lucky there is. Now, for those of you that are familiar with linearization, you understand that this is not a magic solution, right? There are some compromises that we have to make in order to perform linearization. Specifically, our linearized form of our function is only going to be valid for a small range of values. But diving back in, let's say we have a function that looks like this. It is nonlinear, okay? And what we can do is we can define a linearization point, which I'm going to call x0. Generally, this is going to be some point of interest. It could be near the nominal operating value. It could be near the edge of stability. But it's some area, some state near which we're interested in that local behavior. And linearization, the way that it essentially works, you can see here we're blowing up this little piece, is that although the function is curved, when we zoom in far enough, the tangent to that function is a relatively good representation of it locally. But if we extend that out, you can see the gap here becomes larger and larger. So the tangent to the function at x0 has a slope defined by dy dx. And for a small region around x0, the linear and nonlinear functions give very similar values, with a delta y being relatively small. And that delta only continues to increase as we move further and further out. So, let's take a look at this in a more mathematical fashion. To perform linearization, we have to assume we know what the relationship is between x0 and y0, right? If we have a defined function, that shouldn't be a problem. We can take our x0 and we can calculate y0. What is the intersection right here, right? We need to know x0 as well as y0. We call this our linearization operating point, from which we can project our model linearly according to the slope. We could potentially solve for other estimates nearby. So we know what the pair x0, y0, what those values are. But if we want to move slightly to the right or slightly to the left, let's say we have x0 plus a small value, then we could adjust our y value accordingly. The further away from this linearization point or operating point we try to estimate using our linear model, the less accurate our estimates will be. The most accurate estimate would be very close to the operating point on the x-axis. And that makes sense because the ideal solution would be to lie right on top of that point. As such, we generally define a linearization region around our operating point, where we predict that error is acceptable. Estimates performed outside of this linearization region would be considered unreliable. We've already said this process is called linearization, and it allows us to represent a nonlinear function as a linear one for this small region. We can take a look at the math here. I'm not going to spend too much time focusing on it, but we can perfectly represent any function for an infinitely wide domain if we know all the derivatives. Okay, first order, second order, all the way to infinite order derivative. And we use something called the Taylor series expansion. So this equation here is not an approximation. This is a completely accurate representation of any function. For any function of x, we can represent it around an operating point by its operating point value. Right here is x0, y0. Then we take the first order derivative. So this is going to be df dx. And we multiply that by the difference between our new x value and the original. Then we take the second order derivative, d squared f dx squared. And we multiply it by the x minus the x0 squared. And we go on and on and on till infinity. Now, if we do that till infinity, we will end up with a completely accurate representation of our circuit. That doesn't really help us too much with linearization, however. If we want to linearize, what we can do is say, you know what, we're going to cut off everything past the first order term, which then is going to turn this from an equality into an approximation. And so that is essentially what we do for linearization. We determine our operating point, x0, y0. We calculate the derivative of our function with respect to x at that point. This is our tangent. This is our slope. And then now we can shift back and forth along that using this term right here. Okay? Where x0 is our operating point and x might be the point that we're actually concerned with. The form shown above is not very helpful because it's still going to be extremely difficult to use and solve. I'm talking about the form where we take the Taylor series expansion all the way out to an infinite number of terms. But like I've said before, we don't have to do that. What if we only keep the 0th and the first derivative components? So the 0th derivative component is this right here, because d0f dx0, right? And then this is the first order derivative right here. This simply just gives you f. Right, we can just keep those components, ignore all the others, and it gives us a linear representation of the nonlinear system. We got rid of our second and higher order equation or terms, and we end up with what could be more simply represented as this right here. I'm going to use y instead of f of x. So y is equal to whatever the operating y value is plus the derivative or the tangent at x0, and then now the difference between our new and our old x value. So remember that x0 and y0 are known or assumed, and df dx can be calculated. And that leaves only two unknown values in this equation, right? And that's x, which will be our input, and y, that will be our output. The good news is that this equation may be easily inverted, allowing us to find x from a corresponding value of y. And that's really one of the main advantages of doing this. For the nonlinear form of the equation up above, it's generally pretty easy to substitute in our x and generate the y. Moving backwards, however, is often a lot more difficult. But for this version here, it's a lot easier. So that's the real strength of the linear approximation. And here you can see an example of that equation inverted, where now instead of knowing x and giving us y, we know y and we're trying to work back to get x. And this makes sense because for many practical engineering applications, you may have a desired output or a desired operation, and you want to work backwards to find out what is the optimal control input which yields the desired output. Here you have another homework problem. This is a linearization problem. Fortunately, you could actually check this directly in MATLAB or Octave Online if you have access to those softwares. So the last section is on troubleshooting and debugging. Those are two of the most valuable skills that you can have as an engineer, but unfortunately, they're pretty difficult to teach. They can really only be learned through practice, and that's why so many engineering education programs rely heavily on labs, because during those labs, that's when you're designing, implementing, building, testing, and a very important part of that process is going to be debugging and troubleshooting when things don't work the way that you want them to. So what I've included here is just a pretty basic homework problem, which I'm going to end with. So what I'd like for all of you to do is to take a look at the design below and figure out what the problem is. Why isn't this working as expected? All you need to solve this problem is to download and review the data sheet for the UA741 op-amp. It's available online. And so let's see how to complete this homework problem. So I've set up this schematic here, and this is correct. Okay, this is the desired behavior. We have an op-amp. It's connected to the positive and negative supplies. The input is supplied right here, and we have an output supplied, or output that's observed at that point, and has one additional resistor that's placed between the output of the op-amp and the actual output of the circuit. And what I tried to do was implement that circuit over here to the right, as shown. Now this is one where I've mapped this desired circuit onto the footprint we see for an actual chip. But there's one or two mistakes in this design, and so I'd like for you to take a stab at it and see if you can determine what those mistakes are. If you find the mistake, you can always throw it in the comments, and that will help other students. So that pretty much brings this section to a close. Like I said in the very beginning, the objective here was just to teach you some important, or let's say review, because for many of you, you've already learned this, review some important topics such as troubleshooting, debugging, problem solving, linearity, modeling. These topics and concepts that we're going to be using over and over again in the upcoming lectures on linear circuit analysis. So hopefully these practice problems have been helpful, and a couple nuggets will come out of this lecture, out of this module, and remind you of some important concepts in the coming weeks.